Alright, so hello and welcome. I'm going to quickly go over another problem before bed. I guess tomorrow we'll put a little more time in. We'll put a lot of time in today. But yeah, so this is an interesting question. One of my favorites, not a favorite, but one I particularly like. It's kind of a classic question. So we were looking at it years ago. The question is trapping rainwater. Oh yeah, very quickly, I want to take a look at the Sudoku solver again. Just because I think I had an idea before. I have an idea again. I think it'll solve. More efficiently. What you can do is, instead of using a depth, I forgot about this. There's a slight thing that we can change here. Instead of using depth, we can say when R is greater than or equal to num rows and C is greater than or equal to num columns minus 1, and remove the depth altogether, if that's still correct. I think if that works, then we have a way to make this slightly faster. Oh. What? Oh, did I make a mistake? Uh-oh. Oh, I deleted something I wasn't supposed to delete. Oops. Ah. Yes, I did delete something else, but wasn't supposed to delete. Okay. See, that's still correct. Oh, we don't need a depth. Ah. I think that might be the issue. No depth required. Which I think saves us a little bit in terms of speed. It's my guess what we're after. Although I realize this is a totally different problem we're looking at for about 3 minutes now. Okay, uses less memory. Less memory usually means a little bit faster, more speed. There we go. Okay. So row, column, and no depth. I don't know if we can go fast in this though. Is that all I got? I guess technically you can transpose the board to like a one-dimensional array or something. And yeah, I don't really know. Actually, that's kind of all I got. And then make a one division to get the row and column values. But okay, I think it's probably it. I mean, maybe there's another thing we can do here with the wraparound, where we can maybe put this logic, the skip logic. I don't know. I think it's a lot cleaner this way. Yeah, I don't know. I think that's all we got. Okay, we'll go on to the next one. But I just wanted to. I realized you could make it slightly better by removing the depth. Maybe you can make these n rows, n columns constants. I mean, that makes things a little bit faster too. I don't think so, but maybe. I don't know. All right, I'm gonna move on to the next thing though. Certainly. Move on to the next thing though. Yeah. I don't actually know. Oh, you do need to terminate early, yeah, because you need to stop modifying the board and return. So that's why I return a boolean. If I could maybe remove one, if I could remove this if statement somehow. But no. No. Alright, anyway, okay. We're gonna move on. Okay, yeah. So, interesting problem. But solving Sudoku. There's got to be a way to do it a little bit faster. So the question we want to look at today is actually the traffic and rainwater question, which is a pretty interesting one. A bit of a doozy to think about. I'm going to just describe it. This video should be relatively short. Half of it's going to be about a different question. Alright, given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after rating. So they give you an elevation map of the height, output 6 above elevation map. Black section is represented by this array. In this case, 6 units of rainwater for the section are being trapped. Height, output 9, height is n, the length 1 ends less than or equal to 20,000, between 1 and 20,000, the height of I is between 0 and 100,000. So the idea is that, you know, here you could see at this elevation, this is the lowest point. So between these two, excuse me, so there's 1 unit of rain after it rains. Here you have 4 units of rain, right? This elevation is 2, this elevation is 3, it takes the minimum. And then here you have elevation 2, elevation 2, and between them there's elevation 1. So very simple. Obviously I've already seen this question, and I've thought about it quite a bit already, so I know the solution kind of offhand, but what you can do is you can take the elevation from left to right, which is an increasing sequence, the maximum elevation up to that point, and you can take the maximum elevation from right to left, and also a non-decreasing sequence. And at each particular point, if you take the maximum from the left and the maximum from the right, and you take the difference between if you take those two maximums, take the minimum of those two decreasing sequences or non-decreasing sequences, and then take the difference of that minimum with what's present there, that'll give you how much water should be there. So, for example, inside here you see the maximum on the right is 3, and at all of these points it's still 3, and on the left side the maximum is 2, and all of these points it's 2. So the minimum between 3 and 2 is 2. So the water is going to go all the way up to the lowest point. It won't go further than that, right? So let's take the lower of the 2 at each of these points. So it's going to be 2 at each point, and then you can take the difference between 2 and the actual elevation to figure out how much water there should be there. So here there's 2, here there's 1, here there's 2, here there's 1. Because the elevation is 1, 2 minus 1 is 1, 2 minus 0 is 2, 2 minus 1 is 1. And you can actually optimize this slightly by in terms of memory. So what you can do is you can say, all right, what we're going to do, now this is like a really clever thing, really tricky thing. Because you're using non-decreasing sequences, you actually can initialize a left and right height. So L height, I'll go LH and RH. And what happens is you can sort of have a closing window type of algorithm where the left and the right values, because you know these values are non-decreasing, you can compare them to each other, and you could say, okay, if the left side is smaller than the right side, we don't need to figure out what the right side is once we get here, because the left side is already smaller, and we know the left side at that point. So we can consider that to be the correct value at that point, the left height, and then you can say, okay, that's the left height is the smaller value, then you can take the difference between that left height and the actual elevation there, and that's how much rain should be there. And then you can go to the next spot and update the left height according to what's there, and then repeat. And then so here you would have left and right are equal, so you have 0, go here, left is still 1, they're still equal, you use 1, 1 minus 0 is 1, progress again to the next side, so it's 2, 2 for the left side is greater than 1 on the right side. Now we don't necessarily know, now we can process the right side because the right side's smaller. So we process the right side, and we said right is 1, 1 minus 1 is 0. Next we have the right side is 2, Now they're equal to each other again. We could process the left side again. We get 0. On this side, they're still equal. Process the left side again. We get 1, 2. So 1, 1, 2, 1 as expected. Finally, we're 3 and 2. Now process the right side 0. Process this, and we're still 2 all the way across here. So 1, 0, and then finally 3 and 3 minus 3. You get 0. So the loop is just going to be left and right values moving closer and closer, and once they're equal to each other, you also process that portion, but you only need to keep track of the left and right positions and the left and right elevations, so you just keep updating as you go, and just move one or the other closer to the middle, and return what you get at the end. So it looks something like this, and it's very straightforward to code this, by the way. So hopefully we don't make a mistake. Or actually, maybe not that straightforward. We're going to call this instead of h, we're going to call it h instead of height. So we're going to say int r equals 0, L equals h dot size minus 1, while 8r is less than or equal to L. We're going to also have r height 0, left height 0. We're going to say if left height, so actually it should be right height of r and left height of, or excuse me, I did this wrong, it should be L is 0, R is right height, left height is h of L, right height is h of R. And we're going to say if left height is less than or equal to right height, then we're going to increment the ret difference between the left height and the and the height of the left height. Otherwise, we're going to process the, so we're going to say process left side, otherwise process right side. At the end of it, return ret. The left side, we say, now we're going to increment L, and we're going to say if L is less than, now, if L is less than h dot size, then we can update left height equal to L is less than h size, and h of L is greater than or equal to LH, or is greater than LH. Then we update LH to h of L. We do the same thing on the other side, except it's going to be R on each side. So we do right height minus height of R. Then we say R is less than h side, or greater than or equal to. So the left is going to, it's greater than or equal to 0. It should be. And we're going to say h of R is greater than R of H. Update R of H to h of R. And that should be it. And here we're going to decrement R. Something kind of simple like this. Should be relatively straightforward. Wrong answer. Okay. Really? What? L of H. Okay. L of H is height on the left side, and R is height on the right side. So we say if the left height is less than the right height, which it is, we take the difference in the left height and h of L, which is 0. So you get 0, right plus equals 0. Then we increment the left side and update to the new height, which is if L is less than h dot size, and h of L is greater than L of h, which it is in this case, then we update L of h to h of l. Process so then we say again, so 1 is equal to 1, less than or equal to 1, process that, we add 0. Then we take, oh, I'm sorry, it's the other way around, it's not L of h, it's, oh, no, it is, yeah. I'm so confused now. Oh, it's left less than or equal to right, that's why. I think I made that mistake earlier. Confused with the two. That would have been really difficult to catch. Alright, 1, 100, 1, 1, 2, 2, 2, and then we're going to do 100, 5, 200, 6, a bunch of random numbers, 9, 29, 10, and then 1, 5, 2, 5, 6, 7, 5, 5, 3, 1, 2, 5, 5, 5, 5, 4, 1, 4, 5, 6, something like this, I don't know. Let's give that a shot. How are we doing? 16 minutes? Yeah. I think we can go for it. I think it's correct. I could be wrong, but I think it's correct. Hey, there you go. 100%. Yeah, not bad. Okay, sweet. Done. Obviously, I had a lot of issues trying to figure this out the first time around. Solving this in Python, I think, yeah, over 2 years ago. Almost 3 years ago now, I was working on this. Wow. Oh man, I could cry. Just thinking about how quickly time passes. Yeah, well, there you go. Done. Done. QED. QED, ladies and gentlemen. That's the quick explanation. Hopefully that makes some sense. Thank you for watching. Talk to you soon. Have a good rest of your day. I just wanted to revisit this problem because I think it's interesting. I'm going to go to sleep. I think tomorrow I'll pick up and work on a bunch of problems. So yeah, take care.